Today, we're going to start with a nice, wonderful math joke. And like almost all math jokes, they're sometimes a little bit corny. But this one says, what did the little acorn say when she grew up? And that's why she says, gee, I'm a tree. We will be looking at geometry today. Geometry. So Module 2 is geometry and measurement. And what I love about geometry is it's very visual. So we'll be doing a lot of visual questions today and a lot of interactive questions. And so first in geometry, we're going to talk about angles. And I'm just going to give you some vocabulary. One thing about mathematics is making sure that our vocabulary is correct when we talk about it. So acute. Acute is a small angle. It's a less than 90 degrees. And you can see I have a picture of an acute angle here. And it says it's 46 degrees. But anything less than 90 degrees is an acute angle. Right angles are exactly 90 degrees. And they are denoted kind of by this square in the angle. And right angles, anyone work with tools? You know, there's tools that can help us to make sure that we're creating those perfect angles when we build. I'm not a builder. My husband is. But at least when he tells me, hey, you need to hold this board at a right angle so that I can screw in this 4x4, I at least know what he's talking about. So we love our right angles in life and in building. Obtuse. Obtuse angles mean more than 90 degrees, but yet less than 180 degrees. So here's our picture of an obtuse angle. And then we do have our straight angle, which is exactly 180 degrees. Okay, angles, we also have some ways to describe pairs or sets of angles. One way is to call them complementary. So complementary angles are angles that form a 90-degree right angle. Okay? And in this 90-degree angle, right now I have it split into two, a 30 and a 60 degree, but we could split this into many. It does not have to be just two angles. It can be as many angles added together to form that 90 degrees. Supplementary angles form a straight line adding up to 180 degrees. So here we have our supplementary angles. And then we have our angles that radiate around a point, okay? And together they combine to 360 degrees. So here we have that circling around a point, adding up to 360 degrees. So those are some more angle terminology. And another corny math joke coming your way, but it does help us. This says, oh, stop it, you are not at all obtuse. And it's because we're talking about complementary angles. Remember, they're complementary in that they make each other feel good, but they're complementary in the fact that they add up to 90 degrees. Okay? So if we have this adding up to 90 degrees, there's no way that the angles could be obtuse. Remember, obtuse is more than 90 degrees. You can give a little applause if you enjoy that math joke. So we do like our math jokes here. All right, so now a question for all of you. Using the algebra and what we just learned, if I know that I have four angles around a point, they measure x, 3x, 22 degrees, and 46 degrees, what is the value of x? And I'm going to set up a poll. Your four choices are A, B, C, and D. So I want you to think about it. Don't type anything in. Let me set up our poll for you to answer what the degree measure of x would be. Okay, I have that poll set up, so when you're ready, feel free to poll in what you think, A, B, C, or D. So we have four angles. They're going around a point. Remember, what degree did it add up to when it went around one point? If it measures x, 3x, 22 degrees, and 46 degrees, what is x? What is X? See, 3 people of you have buzzed in. 4, I'll give you a little bit more time here to think. What is X? All right, seems that everyone has had the chance to chime in. So let's publish the poll and see what everybody thought. I'm not able to publish. Okay, well, almost all of the kinks have been worked out, but not quite all of them. I'm not able to publish our responses, but I will tell you that 5 of you chose B and 1 person chose C. So let's take a peek to see if the 5 of you are correct. And so here we are. If we have a point and we have these 4 angles, okay, we don't know what their degree measures are for all of them, but one of them is X degrees. One of them is 3x degrees. Another one is 22 degrees. And the last one is 46 degrees. So how I would solve this is I would remember if we're moving around a point, we would be totaling to 360 degrees. So I would take that 360 degrees that I know is my total. I would subtract from that the 2 degree measures that I already have figured out, which is 22 and 46. And in subtracting, that's really 88. So I am left with, oh, not 88, my apologies, 68. 68. So 360 minus 68 is 292. So X and 3X, these 2 degree measures add up to 292. So I could say that X plus 3X equals 292 degrees, which means that X plus 3X is 4X equals 292. And in dividing that by 4, I do find that X equals 73 degrees. So nice job. Moving on, we have triangles. Triangles, we look at classifying them in 2 different ways. One way is by side, and another way is by angle. And these can overlap, but we'll take a look at these 2. By side would be the first 3 characteristics here. Equilateral. Equilateral means all 3 sides are equal, and the angles then have to be the same length. So you can see all 3 sides are equal. We denote that kind of with this little slash mark here. Another way to say equal is congruent. And then that means if all 3 sides are equal, their angles corresponding those sides, A, B, C, and E, are all equal. Isosceles means that 2 sides are equal. Again, this is shown by the lines that these 2 sides are equal. Then opposite those 2 sides means the angles are equal. So angles B and C would be equal to each other since their opposite sides, their corresponding sides, are equal. So that's classifying it. Oh, and then our third type is scalene. Scalene means no sides are equal, meaning no angles are equal. And now classifying it by angle. Well, we've heard of these angles, acute, right, and obtuse. Acute means all the angles are less than 90 degrees. Equilateral is one type of an acute angled triangle, but is not the only type of an acute angled triangle. A right angled triangle means you have one angle that is 90 degrees, and we consider that opposite the hypotenuse. and the hypotenuse here is that long diagonal. And then an obtuse angled triangle is where one angle is larger than 90 degrees. And if we remember, I'll have you type in how many total angles, or how much total does the angle degree measure of a triangle. Triangles add up to what degree measure? Go ahead and participate, chat, type in what you know that to be, or what you can figure that out to be. Excellent, 180 degrees. So triangles add up to 180 degrees. So with that in mind, let's look at our triangle UWL here. And we know that sides UW and UL are congruent. And I can measure that, I can mark that here. UW and UL are congruent. If the measure of angle LUW, and we find that by going L to U up to W, is 54 degrees. What is the measure of angle UWL? Okay? Again, I'm going to put a poll up for you here, A, B, C, or D. What is the measure of angle UWL? Okay, 5 of you have polled in. I'm going to try one more time to see if it'll publish our responses. Still not publishing our responses, but this time 5 people have all chosen B, 63, and that is correct here. What we have is we have 180 degrees total in our triangle. We take away the 54 degrees that we know angle LUW equals, and we are left with 126 degrees, which was C. But C is not the correct answer because we have 2 angles that, because their opposite sides are congruent, these 2 angles both have to measure the same. I can call that X degrees. So what I would say, if I have 2 angles that are the same, they have to total to 126. I need to divide that by 2, which I find to be 63 degrees. Triangles. I love triangles. We have so much to talk about with triangles. Triangles perimeter. Remember that perimeter is adding up the lengths of all the sides of a triangle. Perimeter means the same thing when we're talking about quadrilaterals or any polygon. The area of a triangle is 1/2 the base times the height. And then we have this wonderful theorem called Pythagorean theorem. And it's important to note that the Pythagorean theorem is only used in right triangles. Okay? So remember, only when we have this right triangle can we use the Pythagorean theorem. And what it is it says that if we have 2 legs, A and B, the opposite side, the hypotenuse, remember the hypotenuse is opposite that 90-degree angle, then A squared plus B squared must equal C squared. Okay? A very, very famous theorem in mathematics. And there's some specific Pythagorean triples. These are integers that we know always work for A, B, and C. So let's look at one of those. If I have A equal to 3, B equals to 4, if those are the measures of the side length, then we can figure out what C equals. And the Pythagorean theorem, this triple tells us that C would equal 5. Well, let's just see if that's true. We would have 3 squared plus 4 squared equals 5 squared. So what that's telling us is that 9 plus 16 must equal 25. And sure enough, it does. This is a triple that we use often in mathematics. Other triples include the idea of 5, 12, 13, 7, 24, 25, 8, 15, 17. And again, these are just specific integers that always work. And any multiple of these. So 3, 4, 5, if we multiplied it by 2, we would have 6, 8, 10. So we're going to keep looking at Pythagorean theorem here and see if we can't use and apply this in some real-world mathematics. This question here is about buying a widescreen TV. And if you have ever purchased a TV or a computer or anything with a screen, the screen is always measured by the diagonal. So if they're talking about the latest widescreen TV is 80 inches, that means the diagonal of that TV screen is 80 inches. So here's the question I'm going to pose to you, and it's got multiple parts, and we'll be bringing in some of our knowledge from our previous module on ratios. So if I'm buying a widescreen TV, we're going to talk about what the 16:9 factor is. I have an entertainment system stand, though, that measures 4 feet in length. Okay, so you can kind of visualize, here's my entertainment system, and it is 4 feet. Okay, and I want to buy the largest widescreen TV possible. Remember that widescreen TV is measured in the diagonal, but I don't want this TV to hang off the edges. Who would want the TV to be off of their entertainment system? And so TVs, widescreen TVs, have this what they call aspect ratio of 16:9. And what the aspect ratio says is if I have this TV here we'll put rabbit ears on it, pretend it's a really old TV. All right? And so if we have this TV here, for every 16 inches in length, it gains 9 inches in height. Okay, so this is our ratio of a 16:9 for length to height, or length to width if you want. And so my question to you is, what is the largest widescreen TV that I can buy? Okay, so I want you to chat some ideas of how I need to start this. I know my entertainment system is 4 feet long, but how can I figure out the size of my TV given this information? Go ahead and chat some ideas of what you might do. Not yet an answer, just what steps you need to take. Okay, any ideas here? Kay is helping us. She says use the ratio to find the height. So if I have 4 feet then, how am I going to use the 16:9 ratio to find the height? And you're also free to talk if you need to.
Uh, 16:9 equals 4 to x, or 4 to the height.
Okay, so 16:9 is the same. So I think what you're saying here is 16 to 9 is the same as 4 to, we don't know. Now that's in feet. Is there another way that might help us? I see some people saying 16 equals 16 is 8 is 40 inches. So you're doing kind of 2.5 there. I'll give you a hint of how I might start this one. I might realize that 4 feet is also 48 inches. Okay, if I convert this to inches, I might have an easier time than finding the height of this. So instead of 4 feet, let's look at this as 48 inches. Well, if this is 48 inches and we have a 16:9 ratio, we can set this up then as 16:9 equals this ratio then of 48 inches to x inches. Remember, x right now being the height of my TV. So with this new ratio setup, can we figure out what the height of my TV needs to be? So we're looking at 16 to 9 is the same as 48 to what? Excellent, Toby, 27. So I would recognize that 16, if we multiply that by 3, okay, multiply that by 3, I get to 48. So then 9 times 3 equals 27. I could have also cross-multiplied and said 16 times x equals 48 times 9, and figured out that my x then would have to be 27. All right, so now I have this TV, this widescreen TV, that is 48 inches long and is 27 inches high. We'll make sure to keep our labels here, inches and inches. But my question is, I want to know the length of my diagonal, because remember, TVs are given to us in that diagonal. Oh, that diagonal was not very diagonal as I draw it. My apologies. I never said I was an artist. But we can now, using Pythagorean theorem, estimate the length of our diagonal. And excellent job, Ron Mel. 55 inches. That's about the length of our diagonal. Doesn't work out perfectly. It's not a Pythagorean triple, but it is fairly close to 55 inches. And we use that by Pythagorean theorem of a squared plus b squared equals c squared. So I and I'm sure Ronmel and you all out there could say that we could have side A be 48. We would square that. We would add that to 27 squared. And when we figure out 48 squared plus 27 squared, Ronmel, what did you get then for 48 squared plus 27 squared? This one's a little high for me to do in my head, and I'm away from my calculator right now. So 48 squared plus 27 squared equals what? Anyway, 3,033. Excellent. So 3,033. But remember, that equals our c squared variable. So what we need to take with that 3,033 is the square root, and in doing so, we get just a little bit over 55. Nice work. So that was a little bit about triangles. We're going to move on into talking about some polygons. Now, polygons are closed figures whose sides are straight line segments. And we'll be looking specifically at quadrilaterals. Quad meaning 4. This is a 4-sided figure. And the angles add up to 360. And that should make sense to us because when we had a triangle, half of a polygon here, that added up to 180. So if we double those angle measures, we have two triangles put together there, we do get 360 degrees. Now, in general, and I'm going to say this is in general, the area of any polygon, or any quadrilateral, any quadrilateral is base times height. So in looking at this parallelogram, we would have a base, B, and we have to be careful what our height is. Our height is always making sure that we look at just the height of the figure, not the diagonal, not the side length. Okay, so we'd have a base times a height there. Now, the one quadrilateral that follows a little bit slightly different formula is a trapezoid. Okay, so a trapezoid has this kind of different looking thing, but I'm going to show you it is still base times height. We can see the height of our trapezoid given here. But we have two bases, and those bases have different measurements. We can call that B1 and B2. But really, all we're doing to these are finding the average of those bases. So if we take base 1 plus base 2 and divide it by 2, we have found the average length of those bases. We are then multiplying it by the height. So this trapezoid still has an area formula of base times height. We just need to redefine what we look at the bases. So in this, you can see 1/2. 1/2 is that dividing by 2 part right here. So that is the formula, though, for a trapezoid. Again, looking at area. And so I have an interesting quadrilateral, one that you didn't see on the previous slide there. And this quadrilateral here has some different measurements. And we are asked to find the area of the quadrilateral. And note that this figure may or may not be drawn to scale. We never assume in mathematics that things are drawn to scale unless it is told to us that we're drawn to scale. So, some thoughts. We need to critically think, how am I going to find the area of this quadrilateral? What are your thoughts? You can either talk to me, give me some feedback, or you can chat. Or if you want, you might want to draw on the screen and show me some thoughts that you have with this. All right. Illinois, I see you joined us. Welcome. I'm glad you could join us today. We're trying to figure out the area of this quadrilateral. And I'm not sure if people are confused on where to start. For me, there's 2 different strategies to look at this, but I'm going to talk you through a little bit. Why don't you consider this whole outline here a puzzle? And you almost need to think, how could I fit some puzzle pieces in there? I don't know how to find the area with it right now because it's not showing me a very nice base or height. But if I think of it like a puzzle and maybe need to cut it up into some smaller pieces, I might be able to find that base or height. And see that someone has chimed in with an answer from A, B, C, or D. Okay, Katie, you want to turn it into a square. And I'm going to think by square you mean maybe like this, and it's actually going to be a rectangle. Is that what you're talking about? Yep, rectangle. Good. So if we turn this into a rectangle, we would have a base of 14 and then a height of 16. Okay, well that's going to help us, but what about these pieces right here? What do we need to do with those pieces? Because they're not part of our quadrilateral of this rectangle. What are your thoughts? How are you going to find this? Okay, so we're going to take them into triangles and subtract them. Katie says the area of the rectangle is base times height. Great, so the area of the whole thing we're going to start by saying is 14 times 16. And then Kay is saying something about the triangles. Kay, do you want to help us? I see someone's drawing in some information. Go ahead and try to talk me through this, what you're talking about with these triangles.
Well, we use the formula for a triangle, 1/2 base times height, or base times height divided by 2, and find the area of each one of them. So if we do the top one, okay.
Okay, so with the top one, what are we finding the area? If we have a base of 10 and a height of 14, what is the area of that then?
70.
Perfect. So we have an area of 70. We took 10 times 14 is 140, and then half of that is 70. Okay, and then what about this triangle down here? I saw someone drew in the idea of 6. We got 6 by saying, well, if the whole side is 16, but this upper portion is 10, then this lower portion is 6. We can do the same thing if the whole base here is 14, but we know this piece of it then is 10, so then the remaining part is 4. We would have 6 times 4 is 24, divided by 2 is 12. And would we ever figure out what 14 times 16 equals?
224.
Yep, that's what I got, 224. Ooh, that was really messy. 224 would be the area of the entire rectangle. And then we're going to subtract from it that upper triangle of 70. And we're going to subtract from it the area of the lower triangle, which is 12. So 224 minus 70 minus 12, which would really be minus 82, is 142. B. All right, nice job. Some of you were there ahead of time. Another way, and I'm just going to show this because I want to show that, we sometimes see one solution through things, but there are multiple pathways we can take. Another way that my students took was to take that initial quadrilateral and break it down as such. They broke it down into an upper triangle, a lower rectangle, and a left-handed triangle. So there's multiple ways you could do it to solve this problem. Nice problem solving, everybody. Okay, now we're going to look at circles. And in circles, there is an important number that we call pi. It's spelled P-I, and it has that symbol there. But remember, it is a number. 3.1415, 926 takes us out 7 decimal places, but it continues on and on and on and on. It never actually stops. There's no end point of pi. But why pi is important is it's a unit of measurement that helps us with circles. And so the circumference of a circle, circumference is similar to our understanding of perimeter. It's the distance all the way around the circle. And the distance all the way around the circle is dependent on the diameter. Diameter is this measurement right here that moves through the center of the circle and through, make sure it touches each edge of the circle and moves through the center. The radius starts at the center and touches any edge of the circle, and the radius is also half of the diameter. So a perimeter can be considered pi times diameter, or 2 pi r. 2r is the diameter part, and there's the pi. Area then is pi r squared, taking our radius, squaring it, multiplying it by pi. So with that in mind, let's look at this problem here. It gives us a figure, square PQRS. It says PQRS is inscribed, meaning it is within the circle and it touches each corner of that circle. If the area of the square PQRS is 4, so it's saying the area of the square is 4, what is the radius of the circle? Okay, well first I'm going to pose the question. If we know the area of the square is 4, and remember a square has 2 side lengths that are exactly the same, what is the side length measurement of the square? What is that side length measure? It? Go ahead and type it in there if you figured it out. Good, I see a couple people have typed in and figured out that it's 2. So we said that the area equals 4. And the area is length times width, but in this case, length times width is the exact same. So we could call it really length times length or width times width. So if length times length equals 4, we could say then that our length squared equals 4. And then taking the square root of both sides, we see that the length then equals 2. Okay, so we know that our side measurements are 2, but we want to find the radius. Or what might help us is finding the diameter of a circle as well. So with this side measurement, is there a way to find the diameter? Or is the radius 2? What do you think? What information have we learned today that we could use to find the radius or the diameter of this circle? Maybe you'll need to type or draw. Kay says that the Pythagorean theorem strikes again. It sure does. And for those of you who might not be able to see this, can someone draw in, Kay or another participant, please draw in where you are seeing the Pythagorean theorem and how that's going to help us. All right. And Ronmel is already at the radius is the square root of 2. So let's take a look at where you found that. Okay, so we have the diagonal. We know each side measure is 2. So what we will do is we will use Pythagorean theorem that says 2 squared, our leg squared, 2 squared, plus our other leg squared, 2 squared, has to equal our diagonal squared. So 2 squared is 4 plus another 2 squared is 4, so 8 is c squared, meaning the square root of 8. Square root of 8 here is the entire diameter. But then what we need to do is say, well, the square root of 8 then is our diameter, and so we need to divide that by 2 to find our radius. Now, if you do it on the calculator, Toby got 2.83. If I look at this, I'm not sure what the square root of 8 is, but I know that the square root of 8 is close to the square root of 9. The square root of 9 is 3. So 3 halves, yep, I think it needs to be, Toby, 1.41 looks a little bit better to me. But those of you who might know some upper level math know that the square root of 8 also reduces to 2, the square root of 2. Again, this is something we'll actually be learning in Module 6, not something I would expect you to know right now. So it does equal the square root of 2, or approximately 1.41. Okay, but again, it was Pythagorean theorem helping us out, trying to find that the radius is the square root of 2, or approximately 1.41. Okay, now we're going to consider the same idea with squares and circles, and but we are actually given, we're going to be looking at perimeter this time. And it tells us in this figure, the quarter circle with center D, here's the center of this circle, has a radius of 4. So if it has a radius of 4, then we have this side 4. And this right here is also 4. And ABCD is a rectangle that has a perimeter of 20. And we're going to be looking for the perimeter of the shaded region. So this blue region here, which I'm trying my best to outline, we want to find the perimeter of just that thing. Okay? Well, so what's some information we know right now? We know AB is 4 because AB is opposite side CD, and we've told that this is a rectangle, so we know a rectangle has 90 degrees in it, 90-degree angles, and so we know that that side is 4. We know the perimeter of the entire figure ABCD is 20. So since we know the figure has an entire perimeter of 20, can we figure what the length of BC or the length of AD is? How might you be able to do that? Or someone figured that out? Good. Katie told us 6. And where I'm thinking Katie might come from, or where I'm coming from, is if the whole figure has a perimeter of 20, we need to subtract from that the two sides that we do know, 4 and 4. We have to subtract 8 from it, realizing we have 12 units left. We haven't given this a unit measurement like inches or anything, so we'll call it 12 units left. But then we know that A to D and B to C have to equal the same length, so it must be half of 12 or 6. Okay, so we're getting close. We know that BC equals 6, AB equals 4. What does the measure of AE equal then? Just from A to E. Excellent, 2. So if we already had 4 units used up from E to D, the rest of the units then, 2 is what's left. All right, so right now the perimeter is 6 plus 4 is 10, plus A to E is 12. Okay, but how do we now figure out the rest of this? How do we figure out this portion of the circle? What are we going to have to use? What formula to figure out what the measurement of that portion of the circle is? Bruce, I think you're typing. At least I see something typing. So somebody has chimed in here already. Ron Mel has chimed in, figured out. He thinks it's C. So, in K says circumference. Yep. We're going to go back to this understanding of circumference. Remember, circumference equals pi times diameter, or we can consider our circumference 2 pi times our radius. Okay. Our radius is 4. So our circumference is 2 times 4 times pi, or 8 pi. Okay? 8 pi. But what portion of this circle is being shown? We're only shown 1/4 of the circle, 1/4 of a circle. Remember, that comes directly from the problem. So we need to take that circumference of the whole circle and say we only have 1/4 of it, 1/4 of it, to say what we are seeing for circumference. Measurement of that is 2 pi. So we take our 12 units and our 2 pi units and find out that C, 12 plus 2 pi, is indeed our perimeter of this shaded region. All right. A couple more ideas for you here, and this is getting into some coordinate geometry, looking at what we call the coordinate plane, and it's the distance formula. Now, the distance formula really is the Pythagorean theorem in disguise. What it says is if we're given 2 points, let's call them x1, y1, and x2, y2, and we want to know the distance between these 2 points, we will, in essence, create a right triangle. Okay? And with that right triangle then, we know that we could take the 2 side lengths and square them to find the distance, which we then need to take the square root of. Well, the side lengths then, our horizontal side length would be the difference in our x values. We would take our x2 value and subtract from that our x1 value to find the distance. And notice here I have that x2 minus x1 value being subtracted, then everything's squared, because remember, this is going to become a, in essence, if you want to consider this side a squared, plus b squared. Notice this vertical distance is our y2 minus our y1, the difference between our y values. We're going to take that measurement and square it. It's like our b squared. So down here we have our a squared plus our b squared equals c, which in this case is our distance, but we have to take the square root of it. That is really where this distance formula comes from. It really is Pythagorean theorem. Why don't you give me a yes or a no if that explanation makes sense of where the distance formula is coming from. I've changed our poll to a yes-no. Okay, good. Misty has said yes, I'm following that explanation. Okay, so let's apply the distance formula. Whoops, I already showed you the answer. Forgot to move my star here. Let's take a look at it anyways. Here we have the location of Jen's house and Maggie's houses. We put them on this coordinate grid below. We want to know the distance between those houses. Well, again, we would be looking at using the Pythagorean theorem or that distance formula. What I'm going to see is that my x2, a negative 4, it doesn't matter which point you consider x2 or x1. I'm going to say a negative 4 minus 2 quantity squared. That distance is 6. Okay, so I have a measurement of 6 there. So 6 squared would be 36. I'm going to add to that the vertical distance between our houses, which is 2 minus a negative 6. And minus a negative would be adding then. 2 plus 6 squared, which is 8 squared, has to equal then our distance squared. If we think back to our Pythagorean triple, 3, 4, 5, if we multiply that by 2, we get this distance of 6, 8, 10. This triple that always works. So then we know that the distance squared is 10, so 10 units would be the official distance between Maggie's house and Jen's house. And the last concept for today is looking at the midpoint formula. So again, let's say we have this line, but we want to know the midpoint. We want to know exactly what point is halfway in between those two. Well, if we're looking for something halfway, exactly halfway in between, what we're going to do is we're actually going to use the average this time. So we say that here's our x1 value and our x2 value, and something halfway in between those two. Again, if you think of it just as a horizontal distance, whatever's halfway in between those 2 points has to be the average of those, which is where we get this first coordinate of x1 plus x2. Same thing in our vertical distance. That point has to be halfway in between, and so that's where we get our midpoint of y1 plus y2 divided by 2. So midpoint really is looking at the average of our 2 given points. So your last task for today is to find the midpoint between Maggie's house and Jen's house. Let's see if you can't use that midpoint formula or visually, conceptually understand what is that midpoint. And that midpoint then would be given to us as an XY coordinate. Okay, so if you're going to type in an answer, look for that XY coordinate. What would that midpoint be? Good. We have a couple people who have typed in that midpoint who found it to be -1, -2. This one works out very nicely. Visually, we can see -1, -2 is right here. It does look halfway in between, but we could also average this and say a -4 plus 2 divided by 2. Well, a -4 plus 2 is a -2. Divided by a 2 is a -1. That's where we get our x value. And then our y value is the average in our y's. So we have 2 plus a -6. 2 plus a -6 is -4. Divide that by 2, and we get -2. So -1, -2 is our midpoint. All right. Well, those are the main concepts in geometry and measurement. We discussed a lot today. Specifically, we looked at triangles and polygons, quadrilaterals, and circles. That helped us looking at area, circumference. Another thing we did is we looked at the Pythagorean theorem. Okay, and that Pythagorean theorem was used in right triangles, very important for us. And the last thing we did then is look at how the Pythagorean theorem is related to the distance formula. And we also then added in the midpoint formula. And so with that, that concludes Module 2, but I am going to stay on for a while to answer any questions you have. I thank you for joining me today for this live lecture for number 2, Module 2. And I thank you for your patience as we navigate this math MOOC together. If you have any questions, I'll open it up now. You can either chat or type in those questions. I'll bring up a new page in case I need to add anything in here. So what questions do you have for me? You're welcome. Thank you for joining us today, Redmo.